Oke, Assalamualaikum warahmatullahi wabarakatuh. Good morning, afternoon, evening, or anytime you watch this video. But in my case, it's already almost midnight here. Okay, here I need to redeem all of my promises. But maybe I think I just need to give you one material. I need to redeem my promise, or in bahasa Indonesia we call it as nyaur ya. I need to redeem the asynchronous material to you. But I think for now, I only need to deliver one subject of the physics, which is sorry. Let me share my screen. Okay, I hope you can see my screen clearly. Today we'll talk about rotational kinetic energy. Okay. On the discussion before about the kinetic energy, we all have already know that kinetic energy of an object is equals to half times its mass times square of its velocity. Yeah, it's true on an object with a simple motion, for example, like this box. Yeah, as you can see, this box is moving on one linear direction, which is this way. Sorry, this way. So, for example, if this box has the mass m kilogram and is moving on this direction with the velocity of v meter per second, the kinetic energy, or the total kinetic energy, the more right term here, is equal to half times m times v squared. Yeah, simple. Just like we have studied before, and maybe all of you have studied on the mid school. Yeah, maybe the maybe the regular mid school or vocational. But now let's take a closer look on this kind of motion. It's a very different kind of motion. We can see that in the object below, the box is sliding linearly, but on the ball or the sphere above, we can see that the ball is rolling. Rolling. What is rolling? I think I think you already know about this instinctively. A rolling object moves in a way like this. So beside the translational motion, I mean translational motion is the linear motion on this direction. It will also have a component of rotational motion here, with the axis in the center of the ball or the sphere. The direction is here. So beside the linear motion here, for example, with the velocity of v, it will also roll. It will also doing the rotational motion in this direction. For example, the what is it? The angular velocity is omega. Let's say omega, yeah, which is omega is equal to v divided by r. Nah, remember that v here is, for example, if you have an outer point here, yeah. No, for example, if you have a point here, yeah, this point will moving relatively to the center of the rotation in this direction, for example, with the velocity of v, the same as the velocity of the the overall translational velocity. I'm sorry, I'm slip of tongue. The overall translational velocity of the ball. So the v here is equals to here, and then the distance between this value of velocity and the center is r, or simply the radius of the object here. So okay, we have the linear velocity of the ball or the object, yeah, linear velocity, and we have rotational velocity of the ball also, which can be decomposed into this, where v is also equal to this v, the same, and r is the radius of the object, or here is the ball. So how about the kinetic energy? Will it be the same as this, which is equals to half times its mass, the mass of the ball, times v square, which is only the translational velocity here? The short answer is big N and big O. You can read it together with me. 1, 2, 3. No, it's not the same. The kinetic energy of the ball is not equal to the half mass of the ball times translational velocity or linear velocity of the ball square. It's not equal to this. So what's the right term? Okay, I will introduce you to one new term here, which is the rotational kinetic energy. Okay, I will depict the previous notation. So the ball moves with the linear velocity of v and has the angular velocity of omega, and the mass, we can say that the mass is m. And as you can remember, in the rotating object, we have the the substitution term of m, of mass, which is more compatible to the rotating object, which is moment of inertia, or in mathematical term we can write it as capital I. Yeah, this quantity is very important here. Okay, let me show you. So the rotational kinetic energy, I will just write it down as AKR, is equals to half times I, or moment of inertia of this object, whatever it is. If it's ball, if it will be equal to, I think, if the ball is solid, is 2/5. Yeah, let's talk about that later. Half times I times omega square, where the omega is angular velocity. And this one is linear to make you remember. So this term here is the rotational kinetic energy, or the kinetic energy due to the rotational motion of this ball. And I need to emphasize this. It's only due to the rotational motion. We still not include the translational motion here, or the linear motion here, which is, we just use the same equation as we have studied before, half times m times v square. Okay, sir, but we already have the rotational kinetic energy here. Why do we still need this term? Okay, not that fast for Kuzo, because because even if you have the rotational kinetic energy, that rotational kinetic energy only describe the energy due or because of the rotating motion, rotating through this axis here. Yeah, but not the linear motion here. It will describe by this kinetic energy term or translational kinetic energy term. So if we have these two terms, how should we use them? Okay, here it is. The total kinetic energy. Oh, I use Ka there, but Ak here. Okay, let me try to be consistent. Let's just use Ka, and not this. Yeah, sorry, my bad. I hope you are not confused by this. The kinetic energy, total kinetic energy of this ball, yeah, or this object here, is equals to kinetic energy due to the translational or linear motion plus, okay, let me move my screen for a bit, plus kinetic energy due to the rotational motion. Or we can elaborate this into half times m times v square plus half times I times omega square. Okay, so this is the total kinetic energy. But remember, we still have the mechanical energy or the total mechanical energy of an object here. The mechanical energy is always equal to the potential energy plus kinetic energy. And this value is always conserved. I have told you on the class before. Okay. So we have already studied this term, the potential energy. Yeah. Potential energy, which is equal to mass times gravitational acceleration times h, or the height or the vertical position of the object. Yeah. And how about the kinetic energy? On the equation before, we only use this term because we only know about the translational motion. But now we have already known about the kinetic energy of rotational motion here. So we need to add up this term. So it will be equal to, let me write it here, it's okay. PE plus kinetic energy translational plus kinetic energy rotational. Because basically these two terms is the same as total kinetic energy. And if you want to elaborate further, it will be equal to m times g times h plus half times m plus v square plus half times m plus omega square. Okay, this is the total mechanical energy. As you can see here, we have the term of potential energy and also the kinetic energy, the translational kinetic energy, and also the rotational kinetic energy. Okay, I hope this is clear enough for you. But don't forget about the term moment of inertia. Moment inertia here could be different for different kind of object. Yeah. For example, moment of inertia of a cylinder, solid cylinder is equals to, okay, I'm not I cannot remember it outside of my head one by one, so it's okay for you. I will give it to you on the exam. Yeah, is equals to half times m times r square, where m is the mass of the cylinder and r is the radius of the cylinder. It will be different if we have the solid sphere or maybe the hollow cylinder or any other object. Basically, a different object will have different moment of inertia. So, in short, to put it shortly, a, a rotational motion or a rolling motion here is influenced deeply by the shape of the object, because different shape will give different moment of inertia. We'll dive down about this after this. Okay, first we talk about this object, the solid cylinder, or you can say it as a disk. You have studied on your homework last week. Yeah. For example, if we have a cylinder with the moment of inertia equals to half times m times r square. Okay, this is the r. Yeah. The total kinetic energy is equals to kinetic energy translational plus kinetic energy rotational. For example, if this cylinder is rolling on that direction, it's not necessarily down to the slope, but it could be on the straight line or even up, or even going up slope or even going up, as long as it has the translational and rotational motion. This term applies. Yeah, and this is the phi and this is omega. Okay, let's elaborate this. The kinetic energy equals to half times m v square plus half times I omega square. Okay, let's substitute. Yeah, kinetic energy, the total kinetic energy will equal to, this one is still the same. And now we can substitute the moment of inertia of the cylinder into this equation. This is half times m times r square. And how about the omega or the or the or the angular velocity? Now I have shown you that the omega or the angular velocity is equals to v or linear velocity divided by r, or the radius of the rolling object. So we can decompose this. Omega equals to v per r. And if we substitute this term into this term, we will have v per r squared. And now, because this is r square, and if we square this term, it will be equal to v squared per r square. We can divide this term directly. See, we will only have mv squared on this term, but it will be different. It's not half, because it's half times half. It will be equal quarter. Half times mv squared plus half times half is equal to a quarter. No. A quarter, yeah, this is the right way to write this down, times mv squared. So the total kinetic energy of the solid cylinder, yeah, is equals to half plus a quarter. It will be equal 3/4 times mv squared. Because if we want to add this up, we could use the commutative nature of this equation. So we only need to add up the half and half and half and and this quarter, and mv squared, let it be. But you need to remember that this term is the translational kinetic energy. It will be always the same as we have studied before. And this one term here is rotational kinetic energy. So when you've been asked what is the translational kinetic energy of the rolling cylinder, you only have to answer by this. But if you are being asked what is the rotational kinetic energy of a rolling cylinder, you can use this term, but simply you can also use this term. It's more simpler than this one term, right? But finally, if you are being asked the total kinetic energy of a rolling cylinder, you just need to add up these two terms, become this one. Okay, I hope you can understand this. Because for next calculation, I will just start here. Now we are moving to hollow cylinder or hoop. Basically, this is a cylinder with a very thin wall. The easy example of this is pipe, or you can use a drum that contains anything from maybe water or maybe oil, yeah. But basically, these two are the example of hollow cylinder. So the moment of inertia is equals to I equals to mr squared. Look, it's different from the solid cylinder. It's 2 times the moment of inertia of solid cylinder. If it has the same mass and also the same square, the same radius. So I will just start at this equation. If you want to prove it by yourself, prove for you. But the kinetic energy, total kinetic energy of a rolling hoop is equals to half times mv squared plus, basically it's the same, half mv squared. This one is the translational term and this one is rotational term. and this one is rotational term. So this one is because the motion here, but this one is because the motion here. Just to make you remember, to make sure that you remember this. Okay, so it's quite simple. The total kinetic energy of a hoop or maybe hollow cylinder is equals to half plus half. It's equals to mv squared. Very simple. And now we move to solid sphere. So the solid sphere basically is a ball which has which 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 is solid. Or we can say there are no hole or hollowness inside the ball or the sphere. It's all solid from inside to outside. Okay, for the solid sphere, the moment of inertia is equal to 2 divided by 5 times m times r squared. And if we start at the final term, I will not calculate this though, so to make this lecture not too long. So the total kinetic energy is equals to the translational term is always half times m times v squared plus the rotational term. You can calculate it by yourself, but here I got 1/5 times m times v squared. Oh, sorry. As usual, this is the translational term, and this one is rotational term. Okay, if we add them up, it will equals to we want to make the divisor of the divisor of the pecahan. What is the English term for pecahan? Yeah. I think I have a brain fart here. I need to translate what is pecahan in English. Oh my God, this is fraction, yeah. So we need to we need to make the divisor of the fraction equal. So we should make this as divided by 10. So here we have 5 divided by 10 is equal to half, right? mv squared plus 1 by 5 is equal to 2 by 10 mv squared. So it equals to 7/10 mv squared. Still simple, but the number is not as simple as this one. So let's continue to one more geometry here. Thin spherical shell. So basically you have a ball with just only thin skin or thin shell. For example, if you have a plastic ball which maybe some of you play with it in elementary school, yeah, you can use it on tarkam. Yeah, so plastic ball is a perfect example of a thin spherical shell. Okay, so the moment of inertia of thin spherical shell is 2 by 3 mr squared. So to put it simply, I will just write the total kinetic energy of a thin spherical shell is equal to, this is the transitional term, is always half times m times v squared plus, here I got just a third or 1 by 3 mv squared. And as usual, this is the translational term, due to the translational motion of the sphere, and this is the rotational term. So let's add them up. So the fraction is, we can equalize the divisor by 6, yeah. So it will equal to 3 by 6 mv square plus 2 by 6 mv square, which is equals to 5 by 6 mv square. This is the thin shell or thin sphere. Okay, so now we need to recapitalize. So if we return to the total kinetic energy of these objects, yeah. The total kinetic energy of the solid cylinder is equals to 3 by 4 mv square, and hoop is equal to mv square, and the solid sphere is equal to 7 by 10 mv square. But for the thin spherical cell, the kinetic energy is equals to 5 by 6 mv square. To make it shorter, yeah, if these 4 objects have the same value of radius, the size is virtually the same, and the same mass. For example, just imagine that this one bulk solid cylinder has the same mass with the hoop. I know it's almost impossible, but consider this as the same. The hoop is very, very heavy, very dense. So if we consider them as has the same mass and also the rotational radius, and it move on the same translational velocity. Let's consider this as the same. If all the vectors are the same, these 4 different objects will have or will possess different values of kinetic energy. And here we can see that these are inflection terms except for hoop. So we can conclude that for the same velocity and the same mass and the same radius. Okay, I need to recharge my laptop. Okay, let me repeat. So if all the object has the same mass and the same radius and rolling at the same translational or linear velocity, hoop will always have the highest kinetic energy, and followed by the kinetic energy of the thin spherical cell, and then the solid cylinder, and then followed by the solid sphere. Or in other words, if we give the same amount of energy to this geometries with the same mass and same radius, it will move with different velocity. But on the contrary, this hoop needs larger energy to move at some value of velocity. So if we give the same input of energy, for example, the same value of potential energy, the velocity, the solid sphere will be fastest because the moment of inertia is very small, and the solid cylinder is the second fastest, and the third fastest is the thin spherical shell, and the slowest will be the hoop. To make you, I think to make you understand the what I mean here, you can see this video. Okay, let's sit at this geeky professor. Yeah, he will try to roll different objects. So okay, the thing that important for you guys is on the, okay, you can always try to look for this video because I will share the material via PDF. You can watch the full video if you click the link. But this one is important. We want to compare these two cylinders. This one is, we can consider it as solid cylinder, and this one is a hollow cylinder or a hoop. Yeah, we don't know the mass, but just see. We can assume that this one is lighter and this one is heavier. But let's see when it rolls. See that the solid cylinder will roll faster than the hollow cylinder or the hoop because of this exact explanation that I have give to you. The solid cylinder will roll faster because let's see. Okay. Because no. Initially, I missed the point. Because initially he put it on the same height. Or in other words, they both have the same potential energy, exactly the same, or the same input of energy. But if we see them rolling, the solid cylinder move faster than the hollow cylinder. Because as you can see again here, the kinetic energy needed to move the or to roll the cylinder is smaller than the kinetic energy needed to roll the hoop. As you can see, this is smaller, significantly smaller. So with the same amount of energy input, the cylinder will roll faster than the hoop. Okay, I hope that you can understand my explanation here. Okay, so I hope that you have understand so you can do this task. Okay, let's say that this is an exercise before you will have a final exam. So I will explain to you the problem. This is a ball with the mass of 1 kilogram. We put it at the top of a slope. And I said here that the vertical height of the ball is 2 meters. What I mean here is the height of the ball is equal to 2 meters. Yeah, it's equal to 2 meters. And we assume that initially the ball is at rest. or not moving. So when the ball start moving, it will gain velocity, or it will accelerate. Up to this, let's consider this as final point, or the bottom of the slope. This is top of the slope, and this is the bottom of the slope. Yeah, it will reach the maximum value of velocity. You have known it from the lecture about the potential and kinetic energy before. If the ball is considered as a point of mass, which is the rolling motion is neglected, we only care about the translational motion. This is the A problem. What is the velocity when it reaches the bottom of the slope? Yeah, this is the A. And B, C, D, you need to consider this ball as a rolling solid sphere with a diameter of 0.5 meter. The diameter of the ball is 0.5 meter. With this fact, and if we consider this ball rolling, not sliding like before, please calculate the velocity and calculate the kinetic energies, both translational and rotational. Okay, I mean, this is rich, yeah. So do this homework and submit it before the final exam. Okay. So I've talked about final exam here and there. So what about the final exam? Okay, the final exam will be conducted on Friday, 24th of December 2021, to be exact, at 13 or 1 p.m. Western Indonesian time. Yeah. So Abraham, if you watch this video, you need to follow the schedule. Yeah. Maybe I think this is 9 a.m. in your country. I think, I don't know. Yeah. And what you need to study. So which is I will give it on the exam, is all of the materials after the midterm exam. So we will not, so I won't give you the problem from the midterm exam. So you only need to, so I will give the problem starting from rotational motion, and then we have rotational dynamic, the torque, and also the moment of inertia. And then we have the rotational motion. Yeah, you know, the alpha, omega, and whatever is this. And then this material of the work, energy, power, and also the rotational kinetic energy. So the deadline will be on Thursday, just before the exam. Thursday, the exam is on 24th, so the deadline of this task is 23 of December 2021, and is on 59 Indonesian time, Western Indonesian time. I think I've started to to get sleepy. I write T on Indonesian. What the hell is that? Okay, so as usual, Abraham, please adjust to your own time zone. Okay. And this is the info for the final exam. So next time we meet, it's on the final exam on Friday. And I will give you the link for the exam later. Okay, so I think we won't use the link, the regular link for the class. I will give the link to you later. Okay, so for now, I think it's enough. Yeah, I will see you later on the exam time. So goodbye. Thank you for your attention if you watch this video. Okay, good luck for your exam and your task and your, I mean your homework. So I can finish this video. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.